So let's talk a little bit about what we know so far from chapter 5. As far as the calculus goes. So if I ask you to take the derivative, for example, find each derivative. And I put a natural log in there. So I want you to find the derivative of natural log of 7x. How do you find the derivative of that?
1 over the inside.
Right, so the derivative of natural log is 1 over whatever's inside times the derivative of the inside. Right, so you treat all natural logs like a chain. Natural log's outside, 7x is inside. So the derivative will be 1 over the inside times the derivative of the inside, which is 1 over x. What if I put a quotient in there? So ln of x squared plus 1 over x squared minus 1. How would you do the derivative of that?
Log rules.
Log rules, okay, good. Good. You just have to confer with each other first. You have some sort of hive mind going on. So, I would split this up. You have division inside, so this becomes natural log of the top minus, because it's division, natural log of the bottom. At this point, you haven't done any derivatives, right? This is just algebra. Now, to take the derivative, the rule for a derivative of natural log says do 1 over what's inside times the derivative of the inside. So 1 over x squared plus 1 times 2x. Minus 1 over x squared minus 1 times 2x. I don't know. We'll still have time simplifying. But 2x over x squared plus 1 minus 2x over x squared minus 1. Good enough. So those are the derivative, right? That's a derivative of natural log. That was the first thing we talked about in this chapter. Then we went on to integrals that give you natural log. So for example, I could ask you to do something like, for example, find each indefinite integral. And I'll give you the integral of, I don't know, 1 over 5x minus 3. How do you do this? Substitution. That was going to be my hint. What do you say? U equals 5x minus 3. And then du is equal to just 5 dx, right? Now, I don't have 5 dx, I have 1 dx. So I put 5 here and 1/5 out here. So what does my integral become? 1/5 integral of all of this is equal to du. And this guy is equal to
U.
So it'll be du over u. And what does du over u integrate to? Natural log. Absolutely. So this will be 1/5 natural log of absolute value u 1/5 natural log of, yeah, you gotta put your u back in. So when you have an x to the first on the bottom, even if there's a bunch of other constants, if you just have x to the first on the bottom, you can do u substitution and turn it into a natural log. What about integral of 2x natural log of x squared plus 4 over x squared plus 4.
Can you split this up?
No.
Sorry.
Well, because it's connected by multiplication, now I'm going to split it up. So if you set u equal to x squared plus 4, then you'll have, what's the derivative of x squared plus 4? 2x, so you have the derivative. But then you have ln of u as well. So you still have a slightly complicated derivative. You could do it that way, but you'd have to make two substitutions. If you set u equal to x squared plus 4 du 2x, this integral will become ln of u over u du.
And we go the other way around.
So ln
ln of x squared plus 4 could be u.
So if you set, instead, because that integral was not quite simple enough for my tastes, I would set u equal to the whole thing ln x squared plus 4. Because then the derivative, for ln, when you do the derivative, it's 1 over whatever's inside times the derivative of the inside. So du is actually equal to just 2x over x squared plus 4 dx. And then this matches perfect. So the integral we got when we used the other u wasn't simple enough. We tried a different one. It works out very, very nicely. Now what happens here? So this will become the integral of all of this, 2x over x squared plus 4 dx. All of this is du. ln of x squared is u. So all I have is the integral of u du. Which is u squared over 2 plus c, which is ln of x squared plus 4 squared over 2. So the difficulty in these u substitution problems is going to be figuring out what u equals, not actually doing the integral. Usually the integral is easy once you figure out u. Okay. Then we talked about e to the x. That was what we did last time. Find the derivative of each function. Y equals e to the 7x. How do you do the derivative? Yeah, so e is our favorite function in the world. The derivative of e to the 7x is e to the 7x again. But because the inside is more complicated, you have to times by 7. Right? Derivative of the inside, chain rule. E is your outside function, 7x is your inside. So altogether you get 7e to the 7x. B, y equals x e to the x cubed. And do the derivative. Product rule first, chain rule after. Right? Because this is multiplication, when we do the derivative, we have to start with the derivative of x, which is 1, times the same exact function rewritten, plus, keep x the same, and then multiply by the derivative of e to the x cubed. What's that?
X cubed times 3.
E to the x cubed again,
Oh, no.
times what? 3x squared. Because the derivative of the inside is 3x squared. How would you simplify this if you had to? Factor! You make this look a little prettier if you factor it, because there's an e to the x cubed in both of them, right? So I would pull that e to the x cubed out front. You're left with what? 1 plus 3x cubed, right? Because this is x times x is x cubed. I'm sorry, x times x squared is x cubed. So we like e to the x. We like slightly less other bases to the x. So for example, in 5.4, we made it a little more complicated by looking at things like 3 to the x. Remember how the derivative works? If it's 3 to the x instead of e to the x? Yeah, so 3 to the x wants to be e to the x. Right? He wants really badly to have the same derivative as he started with. But he's not quite e to the x, so you need to make up with an error factor of ln3. So if this base is not e, then the derivative will be almost the same thing, but then you have an ln factor in it. So if you had 100 to the x, what would your derivative be? Natural log of 100 times 100 to the x. Natural log of 100 can't be simplified. It's irrational. All right, so what if I make my exponent more complicated? So, E, we'll do something like 2 to the root x. This is my function y. So the derivative y prime will be ln2 times 2 to the root x times the derivative of root x. Right? The outside function ln2, or I'm sorry, the outside function 2, we took the derivative of right here, but the inside function we have to multiply by. So what's the derivative of root x? 1/2 x to the negative 1/2. Right? Because you have to think of root x as x to the 1/2. Say it again?
1/2 root x.
Yes. So we can bring this down a little bit. Simplify it a little bit by bringing it down. Now, the 2 times root x and 2 to the root x are different. Those we can't get. So this guy is one entity, this guy is one entity, and then these guys are each a factor. You could actually combine the 2's. Do you know how you would combine these 2's here?
Times the top of the power rule.
What exponent is this 2? What exponent does this have? 1. What happens when you divide with exponents? Subtract. So if you really wanted to combine these, which I don't know why you would,
Two with x minus 1.
but you'd get 2 to the root x minus 1. I don't know, who knows? Maybe some crazy calculus book writes this. So it's a little simpler. I'm not super concerned with that. I'm more concerned with you just knowing what the derivative of 2 to the x is and then making sure you get your chain rule in there. All right. So your function is tangent of 6 to the sine squared x. So we have lots of chain rule to do. Tangent's your outside function. 6 to the sine squared x is your inside function to start with. So you do the derivative of tangent, which is secant squared. And then what do you put inside the secant squared?
6 sine 2x.
Same thing, right? 6 to the sine squared x times, now you move on to the derivative of the inside, which itself has an out and an in. So the derivative of 6 to the blah is equal to what? 6. So the derivative of 6 to the x would be equal to ln 6 times 6 to the x, right? So the derivative of 6 to the sine squared will be equal to ln 6 times 6 to the sine squared again. All right, just like over here when we did the derivative of 2 to the root x, we got ln 2 times 2 to the root x again. So ln 6 times 6 to the sine squared again. And what? Times the derivative of sine squared, which itself has an inside and an outside. The outside for sine squared is the square. And the inside is the sine. Remember, sine squared is like if you have parentheses, sine parentheses squared.
Mm-hmm.
So this will become 2 sine x cosine. Circle that, but we don't want to do anything. All right. So what about derivatives of logs with other bases? So for example, if I give you the function y equals log base 3 of x, do you remember how this derivative works? This is the very last thing I did. What's that? E. How do I get E? Am I on? Wait, so how do you do this derivative?
1 over another.
Yeah, so it's like the derivative of natural log. The derivative of natural log is 1 over x. But because it's not quite natural log, you need an ln3 factor on the bottom. So it's almost 1 over x, like natural log is, but you get this ln of this guy factor. What about log base let's do, what if I wrote this? Log of root x. You know what to do with that? Yeah, so if I write log with no base, it's 10, it's implied base 10. Okay, so that's one of your, hopefully something you saw in pre-calculus. Log with no base is implied base 10. So you can think of this when you see this as log base 10 of x. So then to do the derivative, you would take 1 over ln 10 times what? Root x. Times 1/2 x to the negative 1/2. Well, making our life a little hard. You could simplify this a little bit. If you didn't like that root, how could you have simplified this in the beginning? Yeah, you could have applied the log rules like this, x to the 1/2. 1/2 comes down in front. Log 1/2 log base 10 to the, of x. Then this derivative is a lot easier because this is, well, a little easier, because this is a constant multiple. So the 1/2 stays since it's a constant multiple, ln 10 on the bottom, x on the bottom. So if you did a little bit of work, you would be able to simplify this. Right, because this x to the 1/2 will go down and multiply with that root x, and it would give you x. Okay. All right. One thing here. Oh no, I knew it. Find each indefinite interval. So what about when you want to take the integral and you have an e to the x? How do you do that? So yeah, the integral of e to the x is e to the x. But if you have a 5 out in front of the x, you're going to have to make up for that with a 1/5. Or if you do it the long way, you would make your u equal to 5x. That's where the 1/5 is coming from, because du is 5x, or 5 dx. And you have to put that 5 in there and then put a 1/5 to balance it out. So that's where this 1/5 is. What about integral of 2 to the x? Right, so the integral of 2 to the x is almost 2 to the x again. Almost. Right, but remember when you do the derivative of 2 to the x, you get an extra ln2 factor. So to make up for that ln2 factor popping out, you divide by ln2. Right, because if you did this derivative, the ln2 would cancel with this ln2 and get you back here. So the general formula I wrote last time, the integral of a to the x is a to the x divided by ln a for any base that's bigger than 0, not equal. But whatever. About what if I wanted you to do, this is kind of off topic, but I'm thinking of it and you should know it, so let me try it. The integral of cotangent theta d theta. Remember that one? ln of something. So if you remember the formula, there's a formula for this. If you don't remember the formula, do you know how to do this? What's cotangent equal to in terms of sine and cosine?
Cos over sine.
Cosine theta over sine theta? And then can you find a u substitution to make in here? If you let u equal sine theta, then du is cos theta d theta. Right? So then my integral becomes 1, well, du over u, because this is du. And I know the integral of du over u is ln of absolute value u. And I just plug back in my u. Absolute value. There we go. We have formula. So for tangent and cotangent, you really don't need to memorize the formulas. You can do a u substitution. If you want, you can memorize them. For secant and cosecant, the integrals were a little harder. I would probably just memorize them. The integral of secant theta d theta was natural log of secant plus tangent. And the integral of cosecant is equal to natural log of cosecant plus cotangent. Oops. There's a negative on this one. That's kind of where we're at as far as chapter 5 goes. I think. Lots to remember, not a lot to remember. This test is going to be brutal. Maybe. I'm not as concerned with bases that aren't E as I am concerned with E in natural log, okay? It wouldn't surprise me if you don't see this ever again in your life, ever seen math. Okay, most of the things we do in math are with E to the x and ln x. So, it's good to know how to derive these for a random problem or for an application perhaps, but for the most part I'm going to be testing you on your knowledge of E to the x now.